Okay, we have seen the basic idea of finite difference approximation. Now let us introduce some nomenclature and let us try to make faster progress. So we are looking at finite difference approximations on a uniform mesh. Okay, so consider a uniform mesh with a spacing of delta x over a space interval of between 0 and capital L. Okay. So we denote the mesh index by I here, and what we mean by this is that f of the value of f at xi. Okay, so that is the location, the x value at the ith mesh index or node, which we write as f subscript I here, is nothing but f of I times delta x. So that is what xi is here, and we can also write f of I plus 1 in the shorthand notation as the value of f at I plus 1 delta x. So that is, instead of writing f of x and f of x plus delta x, we can write it as f subscript I and f subscript I plus 1, and similarly f subscript I minus 1. So using this notation here, we can write the approximation that we got from equation 2, df by dx at x as f of x plus delta x minus f of x divided by delta x. Instead of that, we can write it as f subscript I plus 1 minus f subscript I divided by delta x plus terms of the order of delta x. Similarly, from the third equation, where we expanded f of x minus delta x, we got another approximation for df by dx as f of I minus f of I minus 1 by delta x, plus again terms of the order of delta x are the ones that are neglected. So the neglected part is known as the truncation error. So the leading term of the truncation error varies as delta x, the magnitude of that varies as delta x, and that is what is denoted here as the order of accuracy of the approximation. And we also got a different expression by manipulating equation 2 and equation 1 and 3, those two approximations. We subtracted 3 from 1, and then we got a different approximation, df by dx at x as f of I plus 1 minus f at I minus 1 divided by 2 delta x plus terms of the order of delta x square. Now there is some difference between these three approximations. So this first one is known as the forward differencing approximation, because f of x df by dx at x is given in terms of f of I plus 1 minus fi divided by delta x. The second expression, where the same derivative at the same location is expressed in terms of fi minus fi minus 1 delta x, that is known as backward differencing. And in this, the value of the first derivative at x is expressed in terms of the two neighboring points, f of I plus 1 minus f of I minus 1 divided by 2 delta x. 2 delta x, because the distance between these 2 points is 2 here, we get a central differencing scheme. So forward and backward differencing schemes are one-sided differencing schemes. So that is, you have I and I plus 1 and I and I minus 1. Not whereas this is central in the sense that you have points which are both to the left I minus 1 and right of this. So that is, both sides are being used to express the approximation of this. So these are known as central differencing formulas. Usually central differencing formulas are more accurate than one-sided differencing formulas, but we need both. Okay, central because they are more accurate, and forward and backward are required at the edges of the flow of the computational domain. If there is no point to the right of this point x or point node I, then we cannot make use of the forward differencing. Similarly, at the left edge of a boundary here, we cannot make use of a point which is outside this computational domain. So at the edges, we would like to have one-sided differencing, and in the center we would like to have central differencing. Okay. So one-sided formulas are necessary at the ends of the domain, and we can look at these derivatives that we have forward, backward, central in a graphical way by looking at this function. In this case it is u here varying with x as per this particular curve. It is a fairly smooth variation, and you have your mesh nodes. This is ith node, and then I plus 1, I plus 2, similarly I minus 1, I minus 2, like that, with uniform spacing of delta x. Now we are looking at the derivative dou u by dou x at I at this particular point. So here we have the red line here is the true slope of this particular function at the point I. If you take I plus 1 or I plus 2, the slope is varying, but at the location I here, the red line here is what is the true slope, the true derivative value at I here. Forward differencing is based on the difference between I plus 1 and I. So the value of I here and the value of the function at I and I plus 1 here, if you join them by a line and then prolong it, then you get this blue line. So that is a forward differencing, and the slope of this, the angle with respect to the horizontal, is the approximation of the first derivative as given by the forward differencing. And backward differencing is based on a line drawn between the value of I minus 1 of the function at I minus 1 and I, and that is the green line here. And the central differencing is based on a line which is drawn between I plus 1, I minus 1 value here and I plus 1 value here, and that is this black line given by C, central differencing here. And if you now look at the slopes, so that is the angle that each of the straight lines is making with the horizontal, we see that the central differencing line here is much closer to the value of the true slope. So it is almost parallel to this, which means it is accurate, whereas both f and b, the forward and backward, are at a different angle compared to the true slope. So that indicates a sense of more error with forward and backward differencing schemes that we get as compared to the central differencing. So this is also an indication of the mathematically derived truncation error, which is of second order accuracy in the case of central, whereas f and b are first order. If you go back to the Taylor series expansion here, so the in central differencing, it is this one which is being neglected from this term onwards. No, it is the third derivative which is being neglected, and in the case of one sided differencing, it is the second derivative and terms are being neglected. So if it is a converging series, the second derivative term is likely to be larger in magnitude than the third derivative term. Okay, so that means that we are neglecting a larger amount of error with one sided differencing involving first order accurate schemes here, whereas in the case of central differencing, it is the third derivative. So that is the next term is the one that is being neglected and all the successive terms, and since the next term is smaller than this term, the error involved in the central differencing is less. So that is also another way of looking at these approximations. So there can be these approximations, and we can also get an approximation of even higher order accuracy. We can get a third order or nth order type of thing. So let us say that we want to have, we can have a systematic way of arriving at order of accuracy for a given derivative. In this case, we are going to look at only the first derivative, and we will seek a third order one sided approximation for u of x, okay, at x. Okay. So we will see when we generalize it, the generalized result requires that in order to write this, we need 4 successive points of the mesh. Okay. So, that and this is of this particular form, that is dou u by dou x at I is xi here. So, we are making use of that, and that is this formula here for a one sided third order accurate approximation will involve 4 points, 4 successive points all to one side of I. Okay. So, that is ui plus 1, ui plus 2, ui plus 3, and these are all multiplied by certain coefficients, real coefficients a, b, c, d, and divide this whole thing is divided by delta x, and this whole formula is third order accurate, and therefore, we can write dou u by dou x at I as per this in this particular way. So, that is we seek an approximation for dou u by dou x at I in the form of a ui plus b ui plus 1 plus c ui plus 2 plus d ui plus 3 divided by delta x plus terms of the order of delta x cubed. This makes it a third order accurate approximation. Now, when this is equivalent in a way to writing this approximation, because we have seen that all these Taylor series expansions involve derivatives, first derivative, second derivative, third derivative and all that. So, what this approximation actually implies is that we would like to get an approximate formula which is dou u by dou x at I equal to a ui plus b ui plus 1 plus ui plus 2 plus d ui plus 3 divided by delta x plus 0 times dou square u by dou x square times delta x. Okay. There is this one is not that it is not there, it is there, but it is being multiplied by 0, so that it does not appear in this expression. Similarly, 0 times the third derivative times delta x square, because we divide by delta x here, it becomes delta x square, and of course, you have factorial 3 here, but since it is 0, it does not matter. Here again you have factorial 2, it does not matter because multiplied by this, and a coefficient e times the fourth derivative at x times delta x cube by factorial 4, which can be subsumed in this coefficient here. And when you have an expression like this plus higher order terms, that is the fifth derivative times delta x to the power 4 and all that, this expression equation 7 and equation 6 are equivalent, because they both are saying that du by dx at I is in terms of this ui plus 1, ui I plus 2, I plus 3 like this, plus 0 times this. So, this delta x term does not appear, 0 times delta x square term. So, this also does not appear, and the only term, the leading term that appears is this factor coefficient e still to be determined times d4 u by dx4 at x times delta x cubed. So, this is what, although we are writing it like this, what we are saying is that this approximation is of this form plus higher order terms. Okay. So, now we can rewrite this as we bring this on to this side, a ui plus 1 plus b ui plus all these things equal to dy by dx minus 0 times this, minus 0 times this, minus 0 times this. Okay. So, writing this is okay, but how do we find the values of a, b, c, d? If we can find unique values of a, b, c, d, then we have a formula here, and in order to find this a, b, c, d, what we do is that we expand ui plus 1, ui plus 2, ui plus 3, which are appearing in this formula, in this proposed formula, in terms of Taylor series about point I. Okay. For example, ui plus 1 is nothing but u at x plus 1 delta x, and that we know is u of x plus du by dx at delta x plus d square by dx square at delta x factorial 2 like this. Similarly, u I plus 2 is nothing but u of x plus 2 delta x. So, wherever we had delta x here, we substitute 2 delta x here. So, and if delta x is small, 2 times delta x is also small. Okay. So, and assuming that it is small and it is still convergent and all that kind of thing, we can write ui plus 2 as u x plus dou u by dou x times 2 delta x plus dou square u by dou x square times 2 delta x whole square by factorial 2. And similarly u at I plus 3 is u of x plus 3 delta x, and therefore we can write this as u of x plus du by dx times 3 delta x plus dou square by dou x square at x times 3 delta x whole square plus 3 delta x whole cubed by factorial 3 and so on. Okay. So now we have these approximations, and we replace these things in the previous equation here. So we evaluate this term a ui plus b ui plus 2 like that. So we multiply this whole thing by b, and then this whole thing by c, and this whole thing by d, and then take the sum of all these things, and this will be given finally in this particular form. This will be p u I plus q times du by dx times delta x plus r times dou square u by dou x square times delta x whole square. For example, p will be a here, and then when we multiply this by b we get b plus c plus d. So p is a plus b plus c plus d, and q here will be b plus 2c plus 3c plus 3d. Okay. So in that way we can once we multiply and then put all these things together, we can express this PQ RST in terms of ABCDs. And now we compare this equation with the equivalent expression, equation 8, that we said is equivalent to this approximation here with 0 coefficients here. And so from this we can say that P is equal to 1. So that is a plus b plus c plus d is equal to 1, and b plus 2c plus 3c plus 3d equal to 0, and this will be square here. So this will be 4b plus 9c plus 16d will be equal to 0, and so on like this. So that will give you 4 equations, one for p, one for q, one for r, and one for s. Okay. This p coefficient is 1 and the other 3 coefficients are 0. So it does not matter what this E is, E will come out of the solution because we have 4 equations, that is a plus b plus c plus d equal to 1 and 2b plus 3c plus 4d equal to 0 and 4b plus 9c plus 16d equal to 0 and so on like that. So you have 4 equations and 4 unknowns, and if you solve those things you get a equal to minus 11 by 6, b equal to 3, and c equal to minus 3 by 2, d equal to 1 by 3, and E will be some sort of summation of this that will come out in this way. It does not matter what the coefficient is, this anyway this whole term is going to be neglected. So that will give us the third order approximation, and when we substitute these back into the original equation we can get dou u by dou x at I here as minus 11 ui plus 18 ui plus 1 minus 9 ui plus 2 plus 2 ui plus 3 divided by 6 delta x plus terms of the order of delta x cubed. So this is a third order one sided approximation for the first derivative at I, involving I plus 1, the value of u at I plus 1, I plus 2, I plus 3. And in this thing on a uniform mesh, when we derive it using this Taylor series like this, we will notice that the sum of all these coefficients will be equal to 0. So you have minus 11 plus 9 minus 9, so that is minus 20, and you have 18 plus 2, 20. So the sum of all these things, so that is a plus b plus c plus d will be equal to 0 here. So that is something that that is one quick way of for us to verify that we got the right kind of formula here. So this kind of expression can be derived not just for the first derivative, we can derive it for any pth derivative, and we can do it for any order of q. So it is possible for us to derive a qth order approximation for a pth derivative using either one sided or central things, and the number of points n here depends on what is order of p here and what is order of q. It is equal to p plus q in the case of one sided, and it is 1 less in the case of central differencing. So, this is a general way of deriving a finite difference approximation of some order. In the next lecture, we will try to apply this to an equation and then see what kind of approximation we get. Okay. Thank you.